This is lenses part 2. I'm going to do my utmost best to remember to shift my paper so that you're not looking at nothing while I'm doing a bunch of examples, because that's fruitless. We can mathematically calculate where those images are going to be. We can calculate where those objects are going to be. We can calculate the height of the image. We can calculate the height of the object. Okay, there's just some things we can figure out how much bigger it's going to be from the object to the image. It's not hard. We just got to pay attention to what we're doing. Distance I is the distance of the image, hence I, from the principal plane of the lens. Remember, this is the principal plane. So it's going to be the distance from the center of the lens. The distance of the object, DO, is also from the principal plane. The focal length is the distance from the optical center, so halfway between top and bottom and side to side. This is the optical center. Is going to be where we find the focal length. And notice that we only have one focal length, and that's why I keep saying that it's equal distance. This way is focal length. This is the same as this way. Okay? The height is the height of the image. If it's got an I, if it's got an O, it's the height of the object. And M is the magnification. How many times bigger? And because we're going centimeters divided by centimeters, there's no units. Or we're going meters divided by meters. There's no units. They cancel each other out. So magnification has no units. A magnification value larger than the value of 1 means that the image is bigger than the object. So, the distance of the object is always positive. And if it's negative, we don't have that. DI. If your answer is positive, it's a real image. Okay? And so what happens is the images are on opposite sides of a lens because it's allowing light to pass through. So that's where here's this object, and then we had this image, an object. Okay? The distance between them from here to here, your DI if it's positive. Okay? If it's negative, it's going to be for a virtual image. That only makes sense. If we can't project something through it, which is what we want to do, we want to be able to see it, and it's in front of the lens, then it would be negative. F, if it's a converging lens, it's positive. If it's a diverging lens, it's negative. We saw that back here where we did this part here, this part here. So we can see that the focal points, if it's positive, it's going to be able to have all the lines go through it. But if it's negative, there's a point that's being missed. Okay, so it's not going through. This is a diverging lens with a negative F, and it's a converging lens with a positive F, where both of them are being handled. HI, if it's positive, it's upright. If it's negative, it's inverted. HO is always positive. We always set ourselves up for excess. The object is always in the upwards position, so its height is always positive. It's never negative. The magnification, if it's positive, it's an upright image. If it's negative, it's an inverted image. It's not positive because it's a bigger magnification and negative because it's a smaller magnification. It's positive if the image is upright, or it's negative if the image is inverted. So just kind of rules of thumb, but they help you if you have to decode a question. Let's look. Let's look. A converging lens. Converging lens. Well, that means that F is always positive. Anything else in here about a converging lens? Nope. Okay, so converging lens, F is positive automatically. Okay, stop. Camera. Be nice. Focus on my pencil. Okay. A converging lens has a focal length of 0.22 meters. If an object is placed 0.41 meters in front of the lens, identify the characteristics of the image that will be produced. Do we have to draw a picture? It's a lot of work. There's 3 rules that we have to do. Let's just write down the information that we have. We have that the focal point is 0.22 meters. Stop it. And it's positive, so it's a converging lens. This is a sign that I need to quit recording. And it's placed 41.41 meters in front of the lens. That's the object. The object is placed 0.41 meters. So it's going to be positive. It says identify the characteristics of the image that will be produced. So we know this formula. Focal length is equal to 1 over the distance of the image plus 1 over the distance of the object. And we also know that magnification is equal to distance of the image over distance of the object. So let's just start. What can we figure out? We have the distance of the object. Where behind the principal plane is that image going to be? 1 over F minus 1 over DO is going to be equal to 1 over DI. So let's figure that out. Make sure your units are the same. And we're going to get we get 1 over 2.106 meters. You probably have a different decimal, but that's what we get. One of the things that we need to pay attention to is that we get 2.106 meters to the negative 1. So I'm not sure if grade 11s have been exposed to negative exponents, but in physics, negative exponents means that we're dealing with something in the denominator. Okay? This answer ends up being a positive answer. So if our DI is, we don't know what our DI is. We know that this is 1 over DI. DI is going to be equal to 1 over 2.106 for a value of 0.4747 meters. So the image is going to be 0.47 meters from the principal plane of the converging lens. It's positive, therefore a Positive is for real images. So this is a real image. Okay, well, let's look at this. This formula here, magnification is equal to the image height over the object height, or it's also equal to the distance of the image over the distance of the object. Paying attention that it's a negative value. So let's go back to this. We're going to put our negative value on there so that we don't forget it when we do the math. Now that we have DI, we can figure out magnification. I'm going to go 0.4747 in all of the decimals, divided by 0.41 meters. And we get a value of, bringing down the negative sign from the formula, we get a value of 1.157 blah, blah, blah. What is a negative? What's under the negative? Ooh, a negative m is, there I did it again. A negative m, which is what we got negative 1.157. A negative m is an inverted image. I'm just going to highlight these. Real image and an inverted image. Okay, that's what the negative sign told us. What does the value tell us? The value tells us, because it's greater than 1, that this is a larger image. Okay, this is greater than 1.0. So we can say, identify the characteristics that the image will be. The image will be real, larger, and inverted. Okay? Let's look at this one. A glowing object 4 centimeters tall is placed 2 centimeters in front of a lens. If the height of the inverted image, HI, is produced as 9 centimeters, what is the distance between the object and its image? The distance between its object and its image, well, we need to remember, does it say? I don't know if it's converging or diverging, but it's from the focal point or the optical center out. DO from the optical center out, DI. So what is the distance between the object and the image? Okay, what is the distance between the object and its image? Do I have either piece of this information? Well, let's go back here. It's height, glowing object, height of the original is 4 centimeters tall, always in the positive direction. It's placed 2 centimeters in front of a lens, so the distance of the object from the center of the lens is plus 2.0 centimeters because it's always positive. If the height of the inverted image, it's inverted, so we have to give it a negative, is 9.0 centimeters. What is the total distance between the objects? Well, do I have DO? Yes. Do I have DI? Nope. How do I find DI? HI over HO is equal to Remember here in this lovely formula, HI over HO is equal to negative DI over DO. Okay? If I want to isolate for DI, I'm going to go, I'm going to put the negative sign with my DO. So I'm going to go negative DO times HI all divided by HO. I feel like we should be like the Seven Dwarfs. Hi-ho, hi-ho, to work we go. Okay, back to work. DI, negative 9.0 centimeters times by, well, that's the height, but it's still negative 2.0 centimeters. And we're going to divide that by the original height, which is 4.0 centimeters. Now look, centimeters times centimeters divided by centimeters. I do not need to convert to meters. DI ends up being plus 4.5 centimeters. Ooh, hang on. DI, if it's a positive, it's a real image. Real image. Therefore, it's on the opposite side of the lens. Right? Because it got projected. So that's awesome. Now, how far apart are they? Going back up to my original. DO, 2.0 centimeters, plus DI, 4.5 centimeters. The images are 6.5 centimeters apart. Okay? And just remember, if you have questions, the online Google Meet will be open. You can jump in and I will help you out. Last question. I know, there's lots to this. We're already at, oh, come on, smarten up, camera. And why be blurry there? You can do it. Come on. Be a camera. Focus properly. Oh. Hang on, Harvey. Stop. Okay. A diverging lens. Let me go back to here. What do we know about a diverging lens? What can we say? Well, right here, the focal point is going to be negative. It's going to be negative. That's what we can say right off the bat. Stop. Has a focal length of 20 centimeters. So F is equal to negative 20 centimeters. Where should the object be placed for the image to be virtual and upright and to be half as tall as the object? Well, it's asking us, where should the object be placed when the image is virtual, upright, and half as large? Okay? Magnification is going to be 0.5. So we can look at this in one of two ways. Where do we find DO? 1 over F is equal to 1 over DO plus 1 over DI. Let's just look at this. This says 1 over DI plus 1 over DO. Does it matter? 1 plus 2, 2 plus 1 still gives us 3. Okay, what don't I have? I don't have DI. How am I going to find DI? I've got magnification, and I know that magnification is equal to negative DI over DO. So let's start there. DI is going to be equal to magnification times negative DO. Oh my word, I'm telling you sometimes. Do I get to use the excuse that it's 10 o'clock at night? I mean, just because we're online, I'm still going to be quirky. You guys know that, right? Okay, DO is going to be negative DI divided by M. Do I have DI? No, I don't. But what I can do is I can use a substitution rule. I can go where I have DO and put my DI in there. Yes, no? No, I'm looking for DO. I'm going to do my DI. DI is equal to negative M DO, because that's what I'm looking for. I'm looking for DO. So then I can go, and I can go 1 over F is equal to 1 over DO plus 1 over negative MDO. That's what I can do. Now, how do I get these to be the same thing? I have to go 1 over F is equal to what? How do I get a common denominator here? I have to multiply it by M. M over 1 over DO plus negative M, sorry, I'm going to pull it out, over 1 over negative MDO. Now what do I have? I have 1 over F is equal to negative M plus 1 all over negative MDO. So I can take stuff out of the denominator. Oh, I'm going to show you what I'm doing. I'm going to take stuff out of the denominator because that's just way easier to work with. So negative MDO, I'm just going to multiply MDO, I'm going to multiply MDO, and multiply F, and multiply F, okay? Negative MDO is going to be equal to negative M plus 1 times by F. Now I have everything out of the denominator. Now I can look for DO. DO is going to be equal to negative M plus 1 times F, all divided by negative M. Now, do I have M? Absolutely, 0.5. Do I have F? Absolutely, 20 centimeters. So the distance that the object needs to be placed is going to be negative 0.5 plus 1 times 20, all divided by, hang on, Harvey. Why negative 20 centimeters? Focal length. Focal. A diverging lens. Focal length has to be negative. Oh, how did I forget that detail? Did I forget that detail? Nope, I didn't. It was right there. I forgot to put it here. Oh, pay attention, people. Negatives. Okay, can't forget that. You're going to get a different answer if you do. Negative 0.5. DO is equal to positive 20.0 centimeters. So a virtual image means that it has to be on the same side. A virtual image occurs when the image is found on the same side of the lens as the object. Well, it's here. It's on the 20 centimeters. The focal length, or upright, has to be a positive number, and it is positive. And it has to be half as small, which we said was 0.5. So it's smaller. So this satisfies all those pieces of virtual, upright, and half as tall. So now you're going to try these lovely, lovely practice problems. And remember, a convex lens is a converging lens, and a concave, so a converging lens is like this. So a convex lens is like this. And a concave lens equals a diverging lens. So this is a concave lens. It caves in. Remember the grade 8 hacks? This caves in, so it's a concave. This bows out, so it's a convex, like Bowflex machines, they bow out. Okay. Have fun.